evening, everybody. Welcome to tonight's lecture by Professor Eric Wilcots. A little bit of story about Eric. I've known him for quite a long time now, I think. He's a regular visitor to South Africa for various reasons, mainly astronomy, of course. But his interest in astronomy started when he was very young, and it's become a passion, as it is with most of us, I think. And he's professor of astronomy at Wisconsin-Madison University, and he's also heads up the natural, I've got to get this right, natural mathematical sciences at the university there. His visits to South Africa are primarily for SALT, Southern African Large Telescope in Sutherland, and SCAR, which is under development in Carnarvon, as you all know. And this is his 7th visit to Scifest. So, Eric, we really look forward to looking for these other guys out there, and hope we can make contact sometime. But thank you very much, Eric. We look forward to hearing what you've got to say. Thank you.
Fantastic. Is the mic on? Yes. Good. Down here. Good. Excellent. Fantastic. All right. Thank you for the introduction. Thank you for the welcome. It's great to be back, especially because when I on my way to the airport, when I left my house in Madison, Wisconsin, before I left, I had to turn on the snowblower and get about 8 to 9 centimeters of snow off the driveway. So I don't know. Snowblowers are these crazy little machines that you can push around like this, and they've got these little blades that spin, and they pick up the snow, and then they shoot it up about 10 meters off the driveway. So I come from the northern hemisphere, where we're in the middle of winter, but I get back, it's gonna be warmer. So it's great to be back. So we want to talk about this interesting topic of searching for habitable worlds around other stars. Okay, the notion of finding a planet that is like the Earth around some other star. Okay? So that's really what we're going to, and that's what we're going to talk about tonight as we move along here. So we're going to start, if we could dim the lights a little bit, that would be great. Okay, we're going to start with this picture, and I want you to note, this is an artist's conception. This is not a real picture taken with a camera. This is an artist's conception of an object that we're going to call Kepler 186f. And by the time I'm done tonight, you will understand why it's called Kepler 186f. So this is the artist's conception of this other planet orbiting around another star, and the artist has decided that the planet might have some oceans, it might have some deserts, it might even have some water. It might be very much like the Earth. And to be able to just conceive of that based on science is a remarkable achievement. Okay? And so we're going to talk about that story as we go along tonight. So what do we mean by habitable world? So first of all, we got to define what I mean by something that's habitable. The Earth is obviously habitable because we live here. So here's a picture. Anybody know what this is a picture of? Raise your hand if you think you know what this is a picture of. Ah, Mars. Yeah, it looks very much like the picture right outside the door. Yes. This is a picture taken of the surface of Mars. How many of you, not counting Matt Damon who can grow potatoes on Mars, okay, for those of you that have seen The Martian, how many of you think Mars is habitable? Raise your hand if you think you could go to Mars and live there. You got an optimist in the back? Anybody else? A couple optimists? Okay. Mars is, you're going to go, maybe with the right stuff you could go. Right? The right equipment, you'd be okay? Yeah, all right. If you bring the right equipment, you could be okay. It doesn't have any oxygen. The atmosphere is thin. It's not good. So Mars is not really habitable, but one of the really interesting questions that we think about when it comes to Mars is, was it once habitable? Did it once have conditions that were conducive for life? And the preponderance of the evidence is that, in fact, it did. It was once a very, very wet place early on in its history. And when some place is wet with lots of water, we sort of think the conditions are good there for being habitable. Okay? And so just what kind of life are we going to talk about? I want to make sure we don't get too excited. We're not talking about this kind of life. Okay? Yeah, all right. We're not. I know. You thought this was a talk about Star Wars. Sorry. We're not even talking about these guys. Right? We're not even going to go to dinosaurs. I know. I'm just disappointing it. Well, what we're really thinking about are these little things up here. These are cyanobacteria. Okay, little tiny bacteria. But life has been on the Earth for something like 4 billion years, maybe less than that. And most of that time, the only form of life on the planet was this kind of stuff. Right? And so when we think about habitable worlds, we want to think about this stuff first, and then we can have some fun thinking about these other things. Okay? All right, so we're going to go back in time a little bit just to set the scene. And this is a little bit hard to see, so I'm going to go to the next one, which is a little bit more easier to see, I think. Could we actually take the lights all the way down? I know this would be a little dangerous, but can we do that from up there, or do I do that from down here? It's on a switch somewhere over here? I have all the way down, because this is kind of hard to see. So I want you to go back in time. All right? We're going to go back in time a bit. And we're going to go back in time to a point where we do not have electricity. All right? Where night is really, really dark. You might have a campfire. That's about it. Hey, you don't have a cell phone. You don't have electricity. Okay? But the sky is really, really dark. Really, really dark. And over night after night, week after week, month after month, what you do is you stare at the night sky. Okay? To look for patterns in the night sky. And you see the patterns we're familiar with. You see those constellations up there. But you notice over time that there were a few objects in the night sky that kind of moved around. And this is showing what the path of the planet Mars looks like over the course of about a year. It would sort of march its way across the sky, and then it would suddenly sort of go backwards, and then it would turn around and keep on going in the direction that it went. And the ancients knew of 5 of these objects that did this, that moved across the night sky relative to the background stars. 5 objects. Can you name them? I named them, one of them for you. Mars is one of them. Saturn is one of them. Jupiter is one of them. Venus, I heard somebody say Venus, and what? Yeah? We'll get to Uranus later. Mercury, right? Mercury, Venus, Mars, Jupiter, and Saturn. Those are all planets that you can see without a telescope, and they all do a behavior somewhat like this. They move across the sky. And the ancients knew about this. Okay, we can turn the lights up a little bit now. Get back to where I'm going to keep you jumping up and down. This is going to be great. Okay, so 2,000 years ago, we had a model for how this all worked, right? All these things moving around the sky and how it all worked. And that model lasted for a couple thousand years until this guy, Johannes Kepler, came along. Okay? And Johannes Kepler did a lot of math, but he also looked at a lot of data. Looked at a lot of data of the positions of the planets, particularly Mars, on the night sky. And based on that data, based on observations, he decided, no, we've got it all wrong. The planets, those 5 things that move, and the Earth, all go around the sun. And they all go around the sun in elliptical orbits. They're not perfectly circular, they're elliptical, a little bit stretched out. Okay? And the other thing that he derived from looking at the observations is he came up with a relationship between how long it takes a planet to go around the sun and how far away from the sun it is. So Mars takes longer to go around the sun than the Earth does. Venus takes less amount of time to go around the sun than the Earth does. Okay? And so Kepler discovered what all of my students in my class this semester know as Kepler's third law. They actually have to do math with it, but I won't make you do that tonight. Okay? The relationship between how long it takes the planet to go around the star and how far away it is. So I want you to remember that. Remember Kepler, and remember that he came up with this relationship. So after nearly 400 years, after Kepler, the intervening 400 years, we learned a lot about our solar system. Not just Mercury, Venus, Mars, Jupiter, and Saturn, but we discovered, somebody mentioned, I heard Uranus yelled out. I heard Neptune mentioned. And then, yes, in the 1920s, a fellow by the name of Clyde Tombaugh discovered this other little thing out there called Pluto. That was a planet for a while. Then he said, nah, that's not a planet. Right? We called it a dwarf planet. So we knew about our solar system. We learned a lot about our solar system. Okay? But how many of you were here for the very first Scifest? The very first Scifest? You guys were here for the very first one, 20 years ago. Are you 20? You're not 20 years old. You were not here for the first Scifest. You're 20 years old? What's that? Oh, the very first Scifest, 20 years ago. Yes, okay. All right, woo. Yeah, I was good. Sorry about that. So, 20 years ago, at the very first Scifest, we essentially knew of one planetary system. 20 years ago, we knew one. It's the one we live in. It's ours. Everything we thought about planets and how planets form, how they came to be, was all based on our solar system. Okay? All right? And that's what we knew. We had 4 rocky planets, Mercury, Venus, Earth, Mars, 4 giants, Jupiter, Saturn, Uranus, Neptune, and all these dwarf planets. Well, and then when we think about habitable worlds in the solar system, where else in the solar system might the conditions be good for life? Well, we already talked a bit about Mars. We thought we could go to Mars, maybe, right? Maybe. There's this thing called Titan, which is Saturn's big moon. It's got clouds. It's got liquid ethane on the surface. If anybody in the room has ever taken organic chemistry, it would be a great organic chemistry lab because it's got all that gooey stuff. It doesn't have life, but it's got organic molecules. And then an interesting one is Europa. Okay, Europa is a moon of Jupiter, and we now know that Europa is covered with ice, and underneath that ice is a liquid ocean. Okay? And just recently announced NASA and the European Space Agency are planning to send landers to Europa in the 2020s to see what's there. But in terms of habitable worlds, that's really what we could think about inside the solar system. And remember, 20 years ago, we knew of one. Well, as of 25th of February, you can go to the exoplanetarchive.ipac.caltech.edu, and we now have 1,955 confirmed planets around other stars. 486 multi-planet systems. There are about almost 4,700 possible planets. These are planets that we probably think are there, but we haven't confirmed them yet. And then something like 270 of them might reside in something we call the habitable zone around another star. In 20 years, this is how far we have come and advanced our knowledge of planets around other stars. And so when you look up at the night sky and you see all those stars in the night sky, most of those stars very likely have planets around them. Okay? So that's where we are now. So we can think about, so we think there's all these planetary systems out there. How might they form? How might they come to be? And so we've got this cartoon. I'm going to show you the cartoon. That's the cartoon. Okay? The cartoon is that we start with a big ball of gas in space. Okay? It looks kind of like a cloud. Right? And for some reason or another, that cloud will start to collapse because of gravity. Right? Gravity is the same thing that makes things fall on the Earth. It keeps the moon going around the Earth. Gravity makes things move. It's attractive. So this cloud will start to collapse. And as this thing collapses, it will start to spin a little bit. So it's going to collapse, it's going to spin, and that's going to flatten out into a disk. So now, instead of having this sort of fluffy cloud, we now have a disk that's rotating. And within that disk, as it's spinning around, small solid things will form, stick together, and ultimately grow into planets. And so we start with a cloud that collapses into a disk. Inside that disk, some chemistry happens, And within that disk, we start to form planets, and ultimately we end up with a planetary system like our own solar system. This is the model that we are using. And the great thing about science is that it is based on these types of models, to think about how things might work. And then the challenge becomes, can we go get data? Can we make observations that would say, yes, that's actually how things do work? Right? So we're in that loop. Okay, so here's a picture of these clouds in the galaxy, out in space. These are giant clouds, these dark things you see here. Giant clouds, within them, stars are probably forming. Okay? New stars are forming right now, somewhere else in the galaxy. We also know that in these clouds there are some really interesting molecules. Okay, we can use special kinds of telescopes called radio telescopes to look at molecules in space. These are complex molecules, cyanide, vinyl. I've got vinyl records. Anybody else out there got some vinyl records? I know some of you do. Some of you must do. There's vinyl out in space. Okay? So we see these complex molecules out in space. We see these clouds of gas. And so when we form a planetary system, when we form something like our own solar system, the raw material for complex molecules is already there. We have those ingredients that are already part of the mix. Okay? And so here's that cartoon again. We start with a diffuse cloud. It gets smaller. We call it a dense cloud. It becomes this disk. We form a planetary system. And then the star will die, and we don't want to think about that. Okay. Okay. So this is the big circle. And in here, we will form planets. Okay. Everybody with me on that? Questions about that? If you got questions, raise your hand. Don't be shy, by the way. Questions? Everybody's with me? All right. All right. So this is how we think things work. This is how we think planetary systems are going to form. So earlier last year, a brand new telescope started operating, a telescope called ALMA, the Atacama Large Millimeter Array. Right? And I'll tell you, for the students, the learners in the room, one of the really great things about being an astronomer is that you get to travel the world. It's kind of fun. So ALMA is a new telescope in northern Chile. Okay? It's at an elevation of about 5,000 meters in the driest desert on the planet. Okay? And ALMA is a special telescope because it can look at things like those clouds of gas. And this is an image taken by ALMA of a nearby star called HL Tau. It's in the constellation Taurus. And that's what ALMA saw. And if you remember back to my cartoon, it looks an awful lot like maybe this stage of the formation of a planetary system. Okay, you notice we got a star there, we got a gap in that disk. And if I look at that nice image from ALMA, I've got this bright thing, I've got gaps in that disk. There's a disk of material around this star. It's a young star. Okay? And so if you want to think about what our solar system looked like 4.7 billion years ago, before we formed the individual planets, this is probably what our own solar system looked like. Okay? We've come a long way since then. Right? We've come a long way. Okay, so one of the other interesting things about thinking about this model, this cartoon, is that the process of making a planet is very, very harsh. Because you make a planet by throwing a bunch of stuff together. Okay? You make a planet by bombarding that planet with lots of material, and as you bombard that planet, that's a lot of energy that gets cooked up. And so the models tell us that a planet like the Earth probably starts, and it's very, very hot. It's probably molten material all the way through. Okay? That's what the models tell us. But there is some new data, some new evidence taken from Western Australia that suggests that water on the Earth was present 4.2 billion years ago. Shortly after the Earth formed, there was liquid water on the planet. And so the notion that the Earth became habitable very early on is a very interesting one. Okay, the water might have existed. And this is a picture, a cartoon of what the Earth might have looked like in the beginning. Okay. All right, so now we know something about how planets form. We think we do. We've got an idea. We've got a model. Right? So the next challenge is then, how do we find an Earth-like planet around some other star? How do we go about doing that? And if we do find it, how do I know it's habitable? Okay. So we're going to start with the habitability part two, the things that we think might matter to determine if the Earth is habitable. Without, you guys can already see the screen, but what do you think you would need? What would you want to have on your planet to make it habitable? What? Oxygen? I hear oxygen in here. What was that? Food? Yeah, you need food, yeah. Water? You need some water? Water's good. Gravity's good. Shelter's good. We're going to talk about shelter in a very interesting way. Shelter's good. Anything else you might want? You want water? You want some gravity? Clothes. You want clothes? Remember, we're going to go back to our bacteria, though. Our bacteria probably don't need clothes. Well, I heard something over here. Yes. Warm? You want it to be warm? Yep. Any more? Okay. You need a stable orbit. It's good to have stability. Okay? Yep. All these things are good. All these things are good. So we think there's a number of things. So let's see. Somebody said oxygen. So we're going to need an atmosphere. Right? We got to have an atmosphere. Ours is nicely oxygen rich. It wasn't always oxygen rich. Okay, those bacteria that I showed you a picture of, those bacteria help produce a lot of oxygen. So you and I couldn't be here without having the bacteria that put a lot of oxygen into the atmosphere. Okay? We need liquid water. It's good to have liquid water. A couple things we need to have liquid water. We need to have gravity. We need to be massive enough to hang on to liquid water. And it's great to have an atmosphere that has a little pressure to keep that water liquid. And it's got to be warm enough for water to be liquid. Okay? But it can't be so warm that all the water evaporates away. Okay? So we have to have that just right temperature to be able to get liquid water. And there's some other things in here. Plate tectonics. The fact that we have this crust and we have these plates that are moving, that actually might be essential for the development of widespread life on a planet. We don't know. So we have one example, and that example has plate tectonics. So based on one, but possibly. Okay, so we're going to define the habitable zone. We define the habitable zone around a star as that region around a star where water can exist as a liquid on the surface. Okay? It's a very simple definition. So we're going to define the habitable zone. All right. Not used to exist, because it's Mars, but does exist now and on the surface. Okay? That's what we're going to define. So there are other places in the solar system, like Europa that I mentioned earlier, where there's liquid water underneath the surface. We're not going to call Europa in the habitable zone. There are various factors that can affect the habitable zone, but we're going to stick with this fairly simple definition. So how do we determine this for some other star? So here is the habitable zone for a star. There's a star. Inside the green, it's too hot. Outside the green, it's too cold. That nice green band there is the habitable zone. It's just right. Okay, liquid water can exist on the surface. So here's some math. We're not going to go through a lot of math, but there's a couple things that we need to know to be able to determine whether a planet is in the habitable zone. First thing we need to know is how bright is the star? How much energy is the star pumping out per second? Okay, we call that the luminosity. So we need to know the luminosity of the star. How bright is the star? We need to know how far away the planet is from the star. The farther away you are, the less of that energy from the star you receive. The closer you are, the more of that energy you receive. Right? So we need to know the luminosity of the star, and we need to know how far away the planet is. It's also really helpful if you know how big the planet is, because that tells you how much of that energy you can pick up. Okay? So we need to know luminosity of the star, that's that L in there. We need to know how far away the planet is, that's that D. Those are really the only things that matter. The luminosity of the star and how far away it is. Okay. Atmosphere matters. That will affect things in a bit. All right? But we'll get to that. So if we do this very straightforward calculation for our own solar system, okay, and this is kind of amazing, right? Very straightforward. Take the luminosity of the sun, take the distance to all the planets, do the math, and figure out what the temperature of the Earth is, and what the temperature of all the planets is. It's very simple. Right? So we can do this, and the black circles here on this plot are showing you the temperature we would calculate for the surface of each planet in the solar system, based on that simple math. The yellow is showing you what the temperature actually is on that planet. And you'll notice that, say, for Mercury, we predict this temperature. It's got a huge range of temperatures. Okay, the Earth, we predict that temperature. The Earth's a little bit hotter. Mars, we are right on. I mean, that's perfect. Jupiter and Saturn, Uranus and Neptune, we're pretty darn close. Pluto, we're really close as well. So this method works. Anybody notice something weird? Anybody notice a weird object on this graph? Remember, the black dots is what we calculate. The yellow is what the temperature actually is. If you were to grade my homework on this, which one do you think I got wrong? What's that? Venus. You think I got Venus wrong? I got Venus I predicted that temperature, and that's the temperature on Venus? I got Venus really, really wrong. You might know why I got Venus really, really wrong? What's that? It's a cloud of gas. It has a lot of gas. Venus has a very thick atmosphere. Venus's atmosphere is about 100 times thicker than our own atmosphere. Venus's atmosphere is 95% carbon dioxide. Anybody heard of carbon dioxide? Raise your hand if you've heard of carbon dioxide. Yeah, a lot of people have heard of carbon dioxide. All right? It is what we call a greenhouse gas. Venus has a runaway greenhouse effect. It has so much carbon dioxide in the atmosphere that the temperature of the surface of the planet is that high, much higher than we would predict. Okay? That's why I got Venus really wrong. Okay? But my method generally works. Right? My method works. If I know the luminosity of the star, and if I know... What else do I need to know? Luminosity of the star and the distance to the planet. I can figure out the planet's temperature. And if I know the planet's temperature, I can figure out if liquid water should exist on the surface. I can figure out if it should be habitable. Okay? So if we can calculate the planet is habitable, if we know the luminosity and we know the distance, and it really does help to know the radius of the planet. Okay. All right. So we're getting somewhere. So where are we going to look for habitable planets? We're going to go out, big sky, lots of stars. Where are we going to look? Hey, how are we going to do this? First of all, we might want to ask, are all stars the same? How many of you think all stars are the same? Every star you look up in the night sky is exactly the same. Oh, good. Nobody does. Stars are really different. Stars are really different. So if I go out, and you can do this experiment, right? If I look at all the stars in the night sky, if I look at all the nearest, say, 100 stars to our own, and I make a plot of their luminosity, how bright they are, versus how hot they are, where the hot stars are over here, cooler stars are over here. If I make a plot like that, just plotting the temperature and the luminosity of a star, I get a diagram that looks like this. That most stars will fall into what we call the main sequence. There's some that are up here, these so-called giants. There's a few things down here we call white dwarfs. But there's a range of types of stars. The sun is right in here, right in the middle, which is really good for us. Kind of an average star. There's a lot of stars that are less massive than the sun. These are cooler stars. These are hot stars up here. The hot stars don't live very long. So if we want to think about habitable worlds, let's not bother with the stars that don't live very long. Let's look at the stars that live a long time. So we're going to concentrate on the stars down here, the ones that live a long time. Okay, and so here's the solar system. There's the sun, Mercury, Venus. Ooh, Earth. Look at that, nicely in the habitable zone. Mars, just beyond the habitable zone. If I go to a slightly less bright star, so-called K star, it's got a much smaller habitable zone. If I go to an M star, the smallest stars we know, you get a really small habitable zone. So the habitable zone will depend upon the type of star I have. Okay? Bright stars, habitable zone's very far away. Cool stars, the habitable zone's very close to the star. All right. So now, how do we find stars around other planets? This is really cool. Okay? So remember, 20 years ago, how many other planets did we know about? None. So the last 20 years, how have we changed those numbers? How have we changed those numbers? So I'm going to need 2 volunteers. Hey, can I make it a little brighter in your case? Okay, you get the lights up a little bit. And I need 2 volunteers. 2 volunteers. 1, thank you. 2, thank you. Come on down. Okay. I'm going to move the table out of the way. Gravity, okay? Gravity does work. All right, we'll leave it alone. We're fine. All right, what's your name? Yaljan. Yeah. I'm not going to get to it. Nice to meet you. How are you? And you? Louisa? Louisa. Okay, you guys got to help me with that. You are going to be the sun. He's smiling. He likes that. You're going to get to be the earth. She likes to be in the earth. Okay, so the sun, I need you to stand here. So the earth, I just want you to walk around the sun, please. Yeah, you got to walk around the sun. So this is what we think of when we think of a planet orbiting a star. The planet is just happily moving along, orbiting the star, right? The star is doing nothing. The star is just standing there. But wait. Stop, please, for a moment, Earth. Isaac Newton taught us 400 years ago that gravity is a mutually attractive force. That means if I have 2 objects, they are attracted towards each other. So gravity tells me that as the Earth, you can go around the sun again, please. As the Earth is going around the sun, it is not simply that the Earth is going around the sun, but what I want you to do very carefully is I want you to take a little bit of movement towards the Earth. Wherever it is, you got to move. You have to constantly move towards the Earth. So they're both moving. When a planet is orbiting, it is both the planet that moves, okay, and the sun that moves. And you'll notice in this little experiment, the sun's movement is less than the planet's movement. But they are both moving. So this gives me a little bit of an angle. If I can measure the motion of the sun, if I can measure the motion of the star, then I will infer that there is a planet going around that star, even if I can't see the planet. Okay? That is secret number 1. Thank you very much. You guys can go back. Thank you. Well done. Okay. And so here is a diagram showing you how our own sun has moved over the last 60 years. The sun starts here and it goes around and it is moved. It is sort of wobbling because it has all these planets. And so if you are that other civilization out there in space looking back, I'll get your questions, and you can measure the motion of the sun, of our sun, you would deduce that there were planets orbiting that star. Yes? If you look at a particular star, can you find your way? If you're just looking at it, yeah. But if you go out there and try to come back, can you come back? That can be challenging. But you can do it. Yeah. How's it possible to you mean, I'm not quite sure I understand your question. Mm-hmm. 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 Oh, you're walking around, and you're lost on the ground, and you're looking for stars, and you're trying to understand how to use the stars to get back to where you were. Navigation by stars. It's a neat thing. So, if, for example, you start walking, you notice where a star was. Now you have to take the fact that the Earth is spinning, so that the star will move over the course of the night. It'll appear to move, so you have to think about that. But if you know your star patterns very, very well, that gives you a sense of being able to find your direction. And the early sailors, the first people who put boats and sailed across the ocean, they used the stars to figure out where they were going. They used the stars to know what their position was and how fast they were moving and if they were going in the right direction. And the first people that wandered around used the stars because they're a fixed pattern. And if you stare at them long enough, night after night, week after week, you understand how they change night to night. So then you have that knowledge. Now, you and I, growing up and living in a place with lots of city lights, we don't know the night sky that well. So you take the two of us, you throw us out into the middle of nowhere where there's no lights, and you try to say, all right, where's the stars? Figure out how to get home. There's too many stars. We've never seen them before because we're surrounded by city lights all the time. We would be lost. But if you spend your whole life looking at the night sky, you get to know them really well. You would be able to figure out where you are. Okay, so, yeah. Yep. Well, whoops. It is moving, or because there's so many planets, it is kind of moving around kind of like that. Very slowly. Okay, but it's the motion of the sun is not just because of the Earth. It's because of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And because they are all orbiting, remember they all have different orbits, that means the sun is constantly being tugged a little bit in every direction as those planets are moving. But it's not very much, right? This is the size of the sun, so it's really only moved, basically one size of the sun. It hasn't sort of, crept out really close to the Earth over it. Oh, no, we'll never get that close. We will not get that close. This movement is very, very small. Yeah, very, very small. Okay. So, we need to be able to measure this motion. So, how are we going to do this? One way to do this is something we call spectroscopy. I'm going to take a spectrum of a star. We don't worry about that. But that's going to tell me how fast that star is moving. And a great telescope for doing this is a telescope called SALT, which is the Southern African Large Telescope. It is in Sutherland, South Africa. Anybody been to SALT? A few of you have. Okay. If you get a chance, you should go to Sutherland. It's a great 10-meter telescope. It's really big. It's really, really, really big. Okay. But we can use it to measure the velocities of stars and measure that little bit of motion. And if you do this experiment, and this is sort of a cartoon, what you get are these little red dots. And that tells you over time how that star is moving. And if I can make a plot that looks like this, I say, over time that star seems to be wobbling a bit. And if I can measure that wobble, I then know that there's a planet going around the star. And the really neat thing, there's another example here. Okay, a few more over here. Do I have one more of this nice? No. Let's go back to this one. Do you see this separation here over time between that point and that point? We're going to call that the period. That is the period of the wobble of the star. Okay? So where is our sun? Our sun was right here, right? He was doing that little motion because the Earth was going around him. There was a period to that. What do you think that is the period of? It's the orbit. It is the orbit of the planet. If I can measure this wobble, and if I can measure how long it takes that wobble to happen, I can now measure the orbital period, how long it takes the planet to go around the star. Okay? And if you remember from our friend Kepler, who told us that if we know the orbit of the planet, how long it takes the planet to go around the star, what else do we know? If we know how long it takes the planet to go around the star, we know the distance. We know how far away it is. And if we know how far away it is, and we know the luminosity of the star, what do we know? We know the temperature. Okay? So if I can make these measurements, I can now figure out that, A, there's a planet going around that star. I know its orbital period, and because of Kepler, I know how far away from the star it is. And because I've observed the star itself, I know how bright the star is. I am on my way to finding habitable worlds. Okay. But you say, oh, wait, Professor, wouldn't it just be easier to take a picture? Right? I mean, come on, right? All this motion stuff. Let's just take a picture. Okay? We got these fancy telescopes. Can't we just take a picture? Okay? Well, no, not really. And the reason for that is, this number right here, which is a really small number. Okay? That means if I was standing somewhere else looking back at our solar system, the difference between the brightness of the sun and the brightness of Jupiter is a factor of 1 billion. Jupiter would be 1 billion times fainter than the sun. And it is just really hard to find something that faint around an object that bright. That's the problem with just taking a picture. The difference in brightness between the star and the planet. You know, but that never stopped us. Hard problems never stopped us. And this one's not going to stop us either. There's a way you can do this. There's a really great exhibit out here in the hallway that shows you how you might do it. And we've got a couple of telescopes coming in space that are going to be equipped with special optics to be able to block out the light of the star to be able to directly take a picture of the planet going around it. So when you get a chance, go out and look at the exhibit out there. Okay, so taking pictures is hard. But the one thing we can do and have done is to wait for an eclipse. Let me get 2 more volunteers. Because I need you. Yep. And I actually need somebody bigger. In the hat. Yes. Come on down. Okay, you're my planet. You're the star. Planet, please go around the star. Planet, walk around the star. No, you're the star. You're the star. This is the planet. You got to walk around. You got to walk around. Walk around him. Or stop. Okay. You're sitting out there. You're the observer. Uh-oh, the planet has moved in front of the star. The planet is blocking some of the star's light. Keep going, planet. Stop. Planet is not in front of the star. Star's back to its regular brightness. Keep coming, planet. Keep coming. Stop. Planet is blocking the light of the star again. Keep going. Keep going. Stop. Oh, wait. Can I measure that? Can I measure how much fainter the star gets every time the planet's in front of it? Oh, I can measure that. I can measure the change in the brightness of that star. And if I can do that, you notice there was a period. The planet came by every so often. If I know the period, what do I know? The distance. Now, let me ask you this, for the really clever ones out there. Get right in front of them. Remember I asked for a big star? What do you think determines how much light is blocked by the planet? What do you think makes the most difference? What? Speak up louder. The size. Both the size of the star and the size of the planet. And so if I can do this, if I can make this observations, I can figure out the size of the planet. And that was the last little bit of information I needed. Thank you very much. Good. All right. Okay. Yes. Oh, wait, come back here. Come back down. Come back down. All right. Come back down. I need you two. You come down. Yep, you come down. And you come down. Okay. Star, you're going to be right here. Okay. Planet, you're going to be right there. Planet here. Planet out here. Okay. Now, you are all going on. You're all going to walk around the star, but you're going to go faster. You're going to be the fastest one going around the star. Okay. Go. You go. Fast. 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 Faster. Faster. You go. Not quite as fast. Not quite as fast, not quite. Slow down, slow down, slow down, slow down, slow down. You go very slowly, very slowly, very slowly. It's not quite working well, okay? But not quite working. Whoa, they all sort of going into the star there. All right. Okay. But you get the idea, I hope, right? That if I have a lot of planets, I'm going to get a lot of these going up and downs, right? I'm going to get a lot of them. I have to stare at it a long time to figure out what is what. All right, thank you very much. Good. All right, excellent. Okay. So that actually points out to a very interesting thing. Which how much time do I have, Case? However long I want. Okay. So one of the interesting things is these, we're going to call them transits, when the planet gets in front of the star. Okay, these transits are very fast. So again, if I am standing on some other planet far away from our solar system and I'm looking at our solar system, Jupiter would transit the sun for about 25 hours. That would be how long Jupiter would be in front of the sun. Earth, about 13 hours. That's not a very long time. So there you are. You've got your telescope. You're pointing it at the sun. You want to catch the transit of Jupiter. Right? You want to measure that, and it's cloudy. Ooh, it's cloudy. I can't see it. If I'm looking for Jupiter, I've got to wait 10 years because Jupiter takes 10 years to go around the sun. I got to wait 10 years to come back and try to take that measurement again because it takes Jupiter 10 years to go around the sun. Jupiter will not transit the sun for another 10 years. Ooh, that's tough. That's harsh. For the Earth, it's 1 year, right? I can come back in a year and try to make the measurement again. So it's a tough measurement to make. Right? So here's what we just saw, the experiment we just saw. There is our sun. Raise your hand, sun, please. Raise your hand. Okay, there's the sun. And my first planet, raise your hand. First planet. Who was my first planet down here? One of you was. Raise your hand. That's the little planet moving in front of the sun. We don't actually see the planet. What we see is the brightness of the sun, of the star, go down, come back up, and we see that repeat. And that is the transit. And if we can measure how much fainter the star gets, how deep is this, that will tell us what the size of the planet is. Okay? And because I can measure the period, I know the orbit, I know how far away the planet is, I know the luminosity of the star. I now know the temperature. I can predict what the temperature of the planet should be. Okay? Now, here's a bunch of examples, same idea. Case knew his clue there. That was great. All right, so courtesy of NASA, this grand satellite was launched, and it was called Kepler. Why do you think it was called Kepler? Because its mission was to find planets, right? So our friend Johannes Kepler, from 400 years ago, who taught us about how the planets in the solar system move, now has his name attached to a satellite. And the purpose of this satellite was to stare at this chunk of the sky, and I'll show you, maybe better, easy to see it that way. So this is the Milky Way, lots of stars, and so that's what Kepler was looking at. And basically simply to stare at that part of the sky, to look for transits, to look for how the variability of stars, and to use that to identify planets around other stars. Okay? And so the Kepler mission was designed to do that. Unfortunately, Kepler didn't work completely, but now it's been resurrected. It's got a secondary mission. It's going to be great. Okay? But that is the Kepler mission. And that is what has given us all of those planets that we now know about. Most of them have come from discoveries from the Kepler mission. Okay. And so if my movie works, does my movie work? Cross your fingers that my movie will work. This is what happens when you look at a bunch of stars. And so this does not show the stars. This simply shows the planets that are probably orbiting stars. Right? And you can see there's big planets and little planets. Stars with lots of planets and stars with few planets. Okay? But that is a sense, it's all sped up too, of the diversity of planetary systems that we now know about elsewhere in the galaxy. Okay? It's kind of cool, these working, you just sort of get mesmerized. So this one here, this thing, moving pretty slowly. That one's moving pretty fast. So remember, the planets that are closer will move faster than the planets that are farther away. Right, there's like 3 planets here zipping around. They're all pretty close. They're just flying, right? This one's taking its sweet time going around because it's farther away, while these other 3 are moving pretty quickly because they're close in. Okay? So that is the sense of what we know. So to give you an idea, 2014 was a great year for finding planets. Okay? Fantastic year for finding planets. And so this is part of what we know. Okay, so I've got a bunch of plots up here, which some of them I'm going to skip over. You want to get my lights back on for up to where they were? These are all the, sort of the data from Kepler. I want to show you a couple of ones. This is kind of an interesting one. Okay, so this is showing you here the size of the planet in terms of Earth radius. So this is the Earth. Earth is 1 Earth radius. That's great, right? Astronomers, physicists, we love to make things simple. And so when we can make a measurement in terms of an Earth radius, we're always starting with 1. Makes life easy. Okay? That's the Earth radius there. And this is the orbital period. How long does it take the sun to go around, the Earth to go around the sun? What's the Earth's orbital period? How many days? 364, 365 days, right? So that is 100, 200, 300. It's a logarithmic plot, sorry. It's 100 days, 200 days, 300 days. So the Earth is kind of like out here. There would be the Earth on this plot. Okay? What I want you to notice, look at all of these planets that have orbital periods like 10 days. Those things are flying. Right? They go around their star once every 10 days. What's crazy is you've got something that's 10 times the size of the Earth orbiting its star every 3 or 4 days. That's what I was taught in school about how planets, how the solar system worked is wrong. Okay? Just flat out wrong. Because we didn't teach about planets that were 10 times the size of the Earth with orbital periods of a few days. That was not part of what we thought planetary systems looked like. And now that's the reality. That's what we have to grapple with to see if we can understand. So now this is interesting. So now we have Earth mass, right, and the Earth radius. So, one Earth mass and one Earth radius, we're going to be right around there. Look at all these other planets. Now this is interesting because these lines over here come from geologists. The lines are there to tell us that if I have a planet made out of, let's say, iron, this is how I would expect the radius of that planet to change as the planet for more massive planets. So a really massive planet made out of iron is only going to be about twice the radius of the Earth. Okay, lower mass planet will be a bit smaller. If it's made out of water, it's water all the way through, right? A planet that's 40 times the mass of the Earth will be about 3.5 times its radius. So if I know what the planet is made out of, I begin to understand what type of planet it might be. Will it be rocky like the Earth? That's sort of the dashed line here in the middle. Okay? Is it going to be a big ball of gas, kind of like Jupiter? That's more like this line. Is it going to be this sort of ball of iron, kind of like Mercury? That would be this line. So if I can measure that radius, and if I can measure that mass, then I can begin to tell you what the planet is made out of, to tell you whether it's going to be Earth-like. And what I didn't mention to you, remember when we had the wobble? Remember when we had the wobble up here? What do you think makes the wobble bigger? The more massive the planet is. So a really massive planet will cause a really big wobble in a star. And so if I can measure that wobble, I can measure the mass of the planet. Right? So I can get mass, I can get radius, I can get distance, I can get orbital period, I can get all that, I can get temperature. And so now I can begin to narrow down and say, are there Earth-like planets around other stars? Okay? So there's a bunch of stuff what we know. And what about the habitable zone? So here is another plot, shows this number 1 here. That's how much sunlight we get. So you can sort of think of it as, this is how much sunlight we get. So again, the Earth is out here somewhere. These are a bunch of other planets. Some of them get a lot more sunlight than we do. Okay, these up here get a lot more sunlight. Down here, they get a lot less sunlight than we do. Okay, so we want to find things that get about the same amount of sunlight that we do, because that's going to help us with the temperature. Right? So that's what we want to look at. And so here's another way of looking at it. Here's the temperature, size relative to the Earth, and some of the Kepler detections. Okay? So I'm getting close to the end. And so here are a couple of examples. The pictures that you see of other planets are artist conceptions. We have not yet taken an image of one of these planets. We know that there's a planet there. We know how far away from the star it is. We know what its orbital period is. We know what its size is, but we haven't seen it yet. We've inferred all of that from other observations. Okay? So here's Kepler 69. There's the star. There's Kepler 69b, which is a pretty big thing, orbiting very close to the star. Here's the habitable zone for Kepler 69. Again, that's knowing the luminosity of the star. Kepler 69c, just at the inner edge of the habitable zone. And it's a bit bigger than the Earth. There's the Earth for comparison. It's a little bit bigger. That's promising. Kepler 69c. Kepler 62, a lot of planets in here. There's the star, a bunch of planets inside. Here's the habitable zone. Ooh, look at that. Kepler 62e and f, both in the habitable zone, maybe 2 times the size of the Earth. These are Earth-like planets in the habitable zone of other stars. Okay? I won't read all that to you, but that all points to Kepler 186f. Our best guess to date for a planet that you might say that is very likely Earth-like. It's just a little bit bigger. Not much, just a little bit bigger. There's a 186 system. There's Kepler 186f nicely in the habitable zone. If you had to pick a planet that was like the Earth, you would pick Kepler 186f. Temperature's probably right. The size is right. So it's got gravity, so it probably has an atmosphere. Do we know if it's geologically active? Does it have volcanoes? Well, the geologists will tell us, given a mass, given a radius, it's likely that it still is hot in the inside, and it likely still has volcanic activity. Okay? So we can have a lot of fun speculating about Kepler 186f. So there's our sort of 4 best habitable worlds. There's the Earth, all a little bit bigger. Okay? But more will come. We will learn more and identify more and more potentially habitable planets around other stars in the years ahead. But the next frontier, there's a couple of other frontiers. One is something we call biosignatures. And that is a really neat thing to think about. It said if you were on a planet, if you lived on Kepler 186f, how would you know that life existed on the Earth? If you lived on one of these other planets and you were looking back at our solar system, how could you tell that life existed on the Earth? This is a real question that scientists are trying to understand. What are the signatures of biological activity? What are the signatures of life that we could detect from afar? Okay? And so how are we going to do that? In the upcoming decade, and many of you are prime age to be part of this. There's a couple things that are happening of note. This thing in the upper right-hand corner is something called the 30-meter telescope. It will be the largest ground-based telescope ever built, 30 meters in diameter. Okay? One of the things it will be able to do is take spectra of all of those exoplanets to determine if they have atmospheres and things like that. Okay? Over here on the left is something called WFIRST, the Wide Field Infrared Survey Telescope. It is a mission that NASA will launch in the mid-2020s, and it will be equipped with something called a coronagraph that will block out the light from the star and allow us to directly image terrestrial planets around other stars. And then down here at the bottom right is something you're familiar with. This is Meerkat, but it's beginning of the Square Kilometer Array radio telescope. So when you think about the gaps in those disks and the formation of making, the process of making planets, this is what the next generation of radio telescope is going to be doing. So there's a bright future, but it is my personal belief that we will learn the most about the possibility of life elsewhere and the possibility of habitable worlds and what ones of those planets are and are not habitable if we understand one planet really, really well, and that's this one. We need to understand this one really well so that we can understand all of the other ones. And that knowledge will build off of each other. And with that, we should be able to, at the 40th Scifest, come back and talk about the habitable worlds we know about and the possibilities that life might exist elsewhere. So thank you very much. If you have any questions, I'm happy to answer them. And enjoy the rest of your stay.
Eric, thank you very, very much indeed for a most enlightening and really fantastic talk. We have another activity coming in here very shortly, so I'll take 2 questions from Eric. So if you have a question, please put your hand up now. There's one there.
Yes? Speak up. Yes. So if they are not habitable, you want to know what that means? Or, sorry, repeat your question.
I want to know. I basically want to know.
Does extraterrestrial life exist on those planets that are habitable? We don't know. Okay? We don't know. Because it's hard. But it's never stopped us before. Okay? As they say, the future is understanding those biosignatures. What observation can I make of a planet to come back and say, based on that data, based on that observation, I conclude that there must be life on that object. We haven't gotten there yet. Does it rule it out? Absolutely not. Absolutely not. But, so I want you to remember when I talked about the life we were going to talk about? The life we were thinking about is little bacteria. We can look for intelligent life. People are trying to do that. But to really find life on some other planet, we have to understand what those bacteria do, particularly to the atmosphere of the planet, that would give it a characteristic signature that will say, yes, there's life there. Okay? You're way in the back. You're going to have to yell because these fans are on.
I was wondering if the gravities of the different galaxies do interact with each other.
Do you make a phone in hammer? Can you just yell like that?
Okay,
Just yell.
so, I was wondering if the gravities of the different stars do interact with each other.
Do the planets interact with stars?
And the gravities, the different gravities of the different stars, they do.
Oh, do the gravities of the stars interact with one another? So stars, the answer is yes. Most stars are in binaries. So most stars have some other star that they're orbiting with. Okay? Some stars are in clusters, and there's lots of stars moving around. The sun is pretty isolated. And most of the planets that I showed that we have the Kepler data for, most of them are isolated stars, so they're not interacting with another star. It gets really complicated to think about what happens to planets in a binary star system. Okay? That's a really, really interesting question. And people are thinking about that, working on that. So if you want to join the fun, let me know. We can do some good work.
Okay, Eric, I'm afraid we're going to have to cut it off there. We've got a lot of other people coming in.
Okay.
Eric, I'd like to thank you very, very much. And what
My
I'm
pleasure.
really looking forward to is you carrying on with this topic next year here.
Okay.
So thank you very much
Thank-
indeed.
Thank you. Thank you.